Hello, we are the University of Toronto's Robotics for Space Exploration team, and we are proud to present our 2022 rover platform. This year we focused on improving the arm accuracy through an all-new arm, improving the science payload through vigorous research on methodology, and weight savings on the chassis all around. New this year is our mapping and location capability, enabled by a new suite of sensors, including LiDAR.
This year's mechanical design focuses on durability and robustness, while minimizing weight and size. The carbon fiber rocker bogie and chassis allows for more efficient traversal of uneven terrain by maximizing contact of the wheels with the ground. Furthermore, the chassis is kept level by the differential gearbox as the rocker bogie is angled. This year, the team also experimented with 3D printing thermal polyurethane for wheels. This allows the design of custom infill and tread patterns to optimize driving on desert terrain. The wheels are driven by 4-to-1 gearboxes and brushless motors.
This year, our electrical team focused on the implementation of 3 PCBs. First, we have our high power board for power distribution and motor control. It includes a circuit to display the battery levels on an LED bar graph and 2 relay safety circuitry for the voltage rails. The speed of each motor is controlled through 6 12-bit DACs and use Hall effect sensors with an incremental encoder to control the drivetrain. Next, we have our low power board, which uses 3 buck converters to regulate our voltage rails with an eFuse safety circuit. And lastly, we have our backplane board, which consolidates all the subsystem PCBs into a single physical enclosure to protect them from the external environment while also being accessible and allowing communication via USB.
The robotic arm utilizes 7 motors to achieve 6 degrees of freedom for reaching all areas around the robot. The gripper uses 2 parallel 4-bar mechanisms to ensure pressure is consistently applied perpendicular to the objects it's grasping, and features 3D printed TPU phalanges optimized to maximize surface area contact with objects. This year, we redesigned the arm with a focus on precision and consistency. All motors are now geared with non-backdrivable gears, either worm or lead screw. This will reduce the power requirements and increase arm stability. We are also working on making simulations of the arm system on Gazebo, which will allow us to prototype and test new arm designs and control codebase with high precision physics simulations before putting them into production.
This year's science team has 2 separate systems to tackle rock and soil sample analysis. All soil sample analysis will be done in a light isolated payload in which samples are deposited by the rover arm into a test tube carousel using 3D printed single-use scoops to minimize cross-contamination. Our soil sample experiments rely on microscopy and photonics to examine samples and look for FAD molecules. This is done by exciting the sample and using a PMT to detect the relative concentrations of FAD in a test tube. Rock sample analysis, on the other hand, utilizes a 2-camera system for rock surface microscopy and for NDVI analysis, which allows us to look for relative levels of chlorophyll.
Our software team uses ROS Melodic to communicate between subsystems of the rover, including map, camera, controls, and localization. The rover's drive system is controlled through a PS3 controller interfaced with PS3 Joy. This allows us to execute smooth turns and have controlled acceleration through analog signals.
To ensure our rover can withstand the challenges of uneven terrain, we have created simulations of the entire rover on Gazebo that will recognize areas where improvement is necessary to ideate our drive code on. To determine the rover's exact position and orientation, the software team uses a customized ROS visualization tool which will display accurate measurements from our IMU.
The autonomy subsystem for the RSX 2022 rover has been designed to be modular. This has been worked towards through the development of several mini rover platforms, which have been a crucial effort allowing ongoing development throughout COVID-19. The autonomy stack makes use of an ultra-wide view Ooster LiDAR, an Intel RealSense RGB depth camera, wheel odometry, a GPS, and NVIDIA Jetson Xavier for data acquisition and perception. The LiDAR system is used in conjunction with the wheel odometry and GPS to perform state estimation on the rover using a Kalman filter. And further, data from the camera is used with computer vision algorithms to perform obstacle avoidance while controlling the motion of the rover.
Thank you for watching our SAR and considering us for the URC 2022. Due to local and university regulations, we have only been able to gather together for the past week or so, but all of our subsystems have been designed and built individually remotely, and we are working to integrate them onto the rover platform. Lastly, I would like to thank all of our sponsors, and we we look forward to competing in person once more.